Hello class, this week we are going to be talking about network policy and access services in Windows Server 2008. I'm going to be giving you some extra information besides the one that is in the book, so I highly recommend you to explore these videos that are going to be actually pretty interesting in my opinion. Welcome back, and I hope you enjoyed the videos as much as I do. Routing and remote access services is a role service used to configure and manage network routing in Windows Server 2008. As a software-based router, RAS is recommended for use in small networks that require simple routing directions, but is not recommended for large and complex environments. Along with routing, RAS provides the Dynamic Host Configuration Protocol Relay Agent, that is a functionality for the 2008 networks. Routing, or the process of transferring data across an internet network from one LAN to another, provides the basis for the Internet and nearly all TCP/IP network communications between multiple organizations. It plays a key role in every organization that is connected to the Internet or that has more than one network segment. Routing can be complex, but if you understand some key concepts and terminology, you can effectively configure, monitor, and troubleshoot routing and remote access for your organization. Most enterprise networks employ several common network devices, such as hubs, switches, and router. These three elements, we already talked about it in the past lessons, but I would like to focus one more time on the routers. As its name suggests, a router determines routes from a source network to a destination network, where to send network packets based on the addressing in the packet. Router operates in the OSI layer 3, which is the network layer, which groups data into packets. Because routers operate at this level, they are referred as a layer 3 devices. Routers can be used as follows: to join networks together over extended distances or WANs, and to connect these similar LANs, such as an Ethernet LAN, to a fiber distributed data interface backbone. There are many configurations that you can join for a router. You can use router in many different topologies, the physical layout of the network, and in different network configurations. A simple network routing configuration with a server running the routing and remote access configuration connect two LAN segments, a segment 1 and a LAN segment 2. In this configuration, the router joins two segments. Because the router is directly connected to both networks, which it will have to route packets, there is no need to create static routes to manually instruct the router where packets need to be directed. Then we have a more complex router configuration. Let's say in a scenario where we have three networks, LAN segment 1, 2, and 3, and they are connected by two routers, router 1 and 2. Router 1 is connected to segment 1 and 2. Router 2 is connected to segment 3 and 2. In a more complex routing scenario, such as this one, routing protocols can be used to automatically transmit information about the routing topology and which segments can be reached via which router. There are some of more common routing protocols that I'm going to be talking about. First one, the Routing Information Protocol. It's one of the most long-standing routing protocols. It has been in use since the earliest day of the router networks. Routers that run the RIP, kind of funny name, will broadcast information about available networks on a regular basis, as well as when the network topology changes. Because this protocol is broadcast-based, that is, it sends out routing information in broadcast packets that are transmitted to every router that is connected to the same network. It is designed for use only on smaller networks. Then we have the RIP version 2. It was designed to improve the amount of routing information that was provided by the first version, as well to increase the security of the routing protocol. And finally, we have the Open Shortest Path First, or OSPF, which was designed to address the scalability limitations of the RIP protocol, to create a routing protocol that could be used on significantly larger networks. Rather than using broadcasts to transmit routing information, each OSPF router maintains a database of routers to all destination networks that it knows of. When it receives network traffic destined for one of these destination networks, it routes the traffic using the best route, which is the shorter, that it has information about in its database. OSPF routers share this database information only with those OSPF routers that it has been configured to share information with, rather than simply broadcasting traffic across an entire network. To process traffic, a router uses routing tables to determine where to send the traffic. A routing table contains entries called routes that provide directions toward destination networks or hosts. The IP routing table serves as a decision tree that enables IP to decide the interface and gateway through which it should send the outgoing traffic. The routing table contains many individual routes, and each route consists of a destination, network mask, gateway interface, and metric. You can view the routing table by using either the Routing and Remote Access console or the command prompt. In the Routing and Remote Access console, you must expand the IP routing node, right-click the Static Routes node, and then click Show IP Routing Table. On the other hand, to view the routing table from the command prompt, at the command prompt, key Route Print, and then press Enter. When an IP packets are sent to an IP router, the router reads the destination address of the packet and compares that destination address to the entries in the routing table. One of these entries is used to determine the interface to which to send the packet and the gateway to which the packet will be sent next. Each routing table entry includes the following 5 columns that are described in this part of the lesson. The first column in the routing table indicates the network destination. As the name suggests, this indicates the destination network that this route entry is used to reach. The router compares the destination address of every received IP packet to entries in this column. Entries in this column that are common to most routing tables includes the following: 0000, which represent the default route, which is used when no other matches are found in the routing table. This is the route that we actually were talking about on the review for the midterm, that is used by default gateway configured on client's computer network interface card. Then we have the 127.0.0.0, which points to the loopback address of 127.0.0.1, which corresponds to the local machine. Then we have 224.0.0.0. Entries refer to a separate multicast route. Also, we have a route that is not pretty familiar to find. That is whatever number, and whatever number to 55, which represent a broadcast address. Broadcast address include a specific subnet broadcast address, such as, 192.168.0 to 55. And then we have the 255, 255, 255, 255. That is the limited broadcast address, which is general for all networks and routers. Then we have in the second column the NEC mask, which refers to the subnet mask of the destination network. This information is important because the largest match determines the route or table entry that is applied to the packet. Then in the third column, we find the gateway, which indicates the gateway value for each routing table entry. When a particular route or table entry is applied to a packet, the gateway value determines the next address or hop that the packet should be sent to. Next, you can see the interface value for each routing table entry. When a particular route or table entry is applied to a packet, the interface value specified in the route determines which local network interface card is used to forward the packet to the appropriate gateway. And finally, we have the final column in the routing table, which corresponds to the routing table's entries metric. This column indicates the cost of using a route. If the two routes are identical, the route with the lower metric or cost is chosen over the route with the higher metric or cost. Lower, smaller metrics have precedence over higher, larger metrics, so that a route with a metric of 2 will be chosen over a route with a metric of 10. For the routing protocol RIP that we talked before, the number of hops before the network destination determines the metric. However, you can use any algorithm to determine the metric if you are configuring a route manually.